record this session, y'all. So let me unmute everybody. Now I might have to mute if the feedback gets too much. All right, so today is going to be our last class, basically. So there's one last thing we're going to learn today, and that's using what's called a z-score. And I'll show y'all how that's very helpful. And then what we'll do on Monday is go over the homework. I won't assign a warm-up. Let me let two people just show up before I continue. Two people are joining right now. All right, good morning, y'all. So I'm discussing that today's the last class, and on Monday we'll just go over the homework, and then I'll give you the last assessment. All right, so that way some of you guys may have other classes and things that you got to do. You won't have to worry about our class once you finish the assessment that I'll give you on Monday. And that's basically going to assess everything that wasn't on the last assessment. So that means the box and whiskers, the medians, the quartiles. That means calculating the standard deviation. And then the last thing would be what we're going to look at today, called the z-score. All right, and I'll put a message on the Google Classroom probably tomorrow afternoon just to say what specifically is on the assessment and remind y'all about what I just said, because there's other people who may not have been able to join. Okay, so we're almost there, and I'll probably update all of the assignments at once. But anyway, so what we got here is 5 groups of numbers. Now notice the difference between A and B. B's got this huge number. Just as I said, here comes another entrant. All right, so notice that if you wanted to find the upper quartile, since the median is 20, for A, you'd be in between 30 and 40. Again, the median is 20, so the upper quartile for B would be in between 30 and 10,000. Notice that makes the upper quartile real far away. So you're going to have a huge right box for B. Whereas for A, the left and right box are going to probably be similar, because the lower quartiles for both A and B are both in between the 10s and 20. So what's the effect of having this huge number added to the group of data? All right, so I got this on the board, but just to point that out. Okay, so the box and whiskers for this one probably be roughly equal, whereas this one, because of the space in between 30 and 10,000, the box and whiskers for this one would be something like that. All right, so we're calculating the mean, the standard deviation. You should get the mean to be 24. And I'll tell you the answer for the standard deviation, which SD equals 10.19. I'll go over how to do that in a minute, but let me give you the answer. Some of you guys might have already did this. Okay, and then over here, you add and divide by 5. The mean is going to be 2016, and then the standard deviation, which I'll just use as SD, is 3,933. Now, before I go over how to do this again, notice the difference here. For A, which would have had some roughly symmetrical distribution, the standard deviation is less than the mean. It's less than half of the mean. But look at for B, where we had a huge right skew because of that big number. Notice that the standard deviation is bigger, almost doubled than the mean. So that's one way that the standard deviation can be really helpful as far as what we're doing here. All right, so what you want to do is you want to subtract each data value from the mean. So 10 minus 24, 20 minus 24, 20 minus 24, 30 minus 24, and 40 minus 24. Okay? Now, some of these are going to be negative, and some of these are going to be positive. Right? So we don't want to just add those up and divide, because then we're going to have to deal with these negatives. So we square them, okay? And then you add them up and divide by 5. Okay, so you get the sum of that third column, then you divide by 5. Okay, and that would be 104 rather. Now that's called variance. So this 104, that's called variance. Now, since we had to square the numbers to make them all positive, we use that to get our average. So we call that variance. Now, in order to compensate for squaring the numbers, we take the square root of the variance. And so the square root of 104 is 10.19. And so that means the average deviation from the mean is 10.19. Okay, this is why people have 2 words for average, because you can just say what I just said. You can use the word average and the word mean in the same sentence and convey what you're talking about a lot easier. All right, now I'm going to point out that the symbol that I used here was just the letters SD. Right on, Lisa. Thanks for letting me know, because I definitely can be the one that makes the mistake here. Yeah. The official symbol, though, is this little O with a little curly. And that's called omega. And so this is the symbol that we use for standard deviation, a little O with a little curly thing on top, like a little colic of hair, like a little cap coming off your head. All right? Now, the difference here is you're going to get big numbers, because you got to subtract from this mean, so you're going to have numbers in the thousands. And then when you get here, when you subtract from this mean, you're going to get an 8,000 number. In particular, you get 7984. And then when you square that, you're going to get a huge number. So that's the problem with this one. You get those huge numbers. I mean, I could show you that too, but it's the same thing. Okay? So notice the effect of adding a huge number. Okay? So this would be like you're hanging out at your cafe, your brother gets $10 an hour. Okay, you're older, you get $20 an hour. Your friend you're with gets $20 an hour. You have an older friend who's a manager, he gets $30 an hour. And then another older friend who gets $40 an hour. So these 5 people, right? All of a sudden, your $40 an hour friend leaves and Bill Gates shows up. All right? Okay, so looking at the homework, this morning right before class, I realized that I had set this to the wrong time. You can see, oops, because it didn't show up over here on my end. It would tell me right here, and I didn't see y'all. I was like, well, what did I do? But it didn't affect anything because the links were still valid. All right, so this is what you should have got for the homework. Now, the interesting with A is that mean and the standard deviation appeared to be the same. And that's a little odd. Let me check that. Nope. Okay. Well, the thing about data that's an issue is that you can have populations that spread differently. Okay, so let's say we had anchovies and sardines. Now these are both small fish, right? But sardines will grow a little bit bigger, whereas anchovies tend to stay fairly small. So you can have both of these with a mean of 20. But with anchovies, they're going to be closely grouped together, whereas sardines will be a lot more spread out, even though they have the same mean of 20. Okay, so if we went ahead and marked this off, okay, notice that if we're above the mean, this would be 10 above the mean. And the same thing here. If we're above the mean, the 30 is also 10 above the mean. But notice the height of the bars is different. So if we're going to compare a 30-gram fish, it depends what population we're referring to. For anchovies, a 30-gram fish is pretty rare. But for sardines, that height of that bar is a lot more. For sardines, a 30-gram fish is a little more common. Right? But both of these have the same mean, and for both of them, 30 minus 20 is 10. But 10 above the mean means something different. Relative to anchovies, 10 above the mean is less common, more rare. Relative to sardines, 10 above the mean is more common. Now, what's the difference between these two? The anchovies is spread pretty close to the mean, whereas the sardines are spread out. So in other words, the standard deviation of anchovies is less than the standard deviation of sardines, even though they have the same mean. So because we want to compare populations, we want to create a statistic that takes into account the mean and the standard deviation. How far above the mean is relative to the standard deviation? Okay, that's called a z-score. And I'll show you the formula, but basically we take the data value, which in this case would be 30. We subtract the mean, which in this case would be 20, and then we divide by the standard deviation. All right, so that 10, when we divide by the standard deviation, is going to give us what we call a z-score. Since this standard deviation is smaller, we're going to get a bigger number. Whereas the sardines, the standard deviation is bigger, so we're going to get a smaller number. All right, so notice when we do this calculation, the bigger the number, the more rare. The closer to the mean, this subtraction will get closer to 0. Okay, so I'm explaining what that is. All right, so what that means is the z-score will be 0 here, and as you go this way, it'll get bigger positively. Whereas if you go this way, it'll get bigger negatively. All right, let's actually do some calculations. Let's say we had a mean of 10 and a standard deviation of 1. Okay, well, one standard deviation would be 1 plus 10 and 1 minus 10. So if we want to be one standard deviation above or below the mean, we'd add 1 and subtract 1. So this would be in between 9 and 11. Now, if we want 2 standard deviations from the mean, so what interval would be 2 standard deviations from the mean? Now we're going to add the 1 twice and subtract the 1 twice. So 12 and 8. Okay, and then 3 standard deviations from the mean. What interval would be 3 standard deviations from the mean? So again, if the mean is 10, 3 standard deviations means 3 times 1. So we'll add 3 to the 10, and we'll subtract 3 to the 10. Okay, so these are called the standard deviation intervals. You create them by adding to the mean and subtracting from the mean. 1 standard deviation, you're adding the 1 once, subtracting the 1 once. 2 standard deviations from the mean, you're adding the 1 twice, you're subtracting the 2 twice. That's why you get 8 and 12. 3 standard deviations from the mean, you're adding the 1 3 times and subtracting the 1 3 times. That's why you get 7 and 13. Now the significance of this is if we have a normal distribution, if it's roughly symmetrical, 68% of the data is going to be within 1 standard deviation of the mean. 95% of the data is going to be within 2 standard deviations of the mean. And 99.7% of the data is going to be within 3 standard deviations from the mean. So a z-score of 3 is pretty rare. So that anchovy would have had a z-score of 3. But the z-score of 1 is not quite as rare. So that sardine might have had a z-score of 1. Okay, so that's just getting the idea across. And notice the difference between these 3 normal distributions. So this is just roughly going over the bar graphs. So the height would be the height of the bars. Okay, notice that the blue graph is less wide. So the red graph is more wide, and the brownish yellow graph is really wide. So the brownish yellow graph would have had a larger standard deviation. The blue graph would have had a smaller standard deviation. Okay, although they both have the same mean. Notice right here going down the middle, the mean roughly at 0. Okay, so here's the formula. Now this little x bar, this little x subscript I, that just means the data value. And so the variable x represents the possible numbers in the data set. The subscript just means the first one, the second one, the third one, the fourth one. So this little symbol here with the subscript I, that just means the data value. That's the mean symbol, and that's the standard deviation symbol. So the data value minus the mean divided by the standard deviation. That's how you get a z-score. Okay, and then here's what I was telling you. This is called the empirical rule, those percentages that I mentioned. And this kind of like spreads it out a little bit. Okay, so notice down here on the bottom, the mean in the middle. If you add the standard deviation once, twice, 3 times. Or if you subtract the standard deviation once, twice, and 3 times. Okay, and then notice they kind of did the little calculations of the percentages in between too, right? So you can get the 34 by dividing the 68 by 2, right? And then you know there's 50% above. So you can calculate this by subtracting 34 from half of the 95. Again, it's all here, but if you wonder where that comes from, you won't have to worry about that much sophistication, but just if you're curious, what the heck are those percentages on the bottom? And then notice 99.7%, well, that leaves 0.3%. And then notice when you divide 0.3 by 2, you get 0.15. So very rare do you have something outside of 3 standard deviations when you have a symmetrical central normal distribution. Okay, so now let's go ahead and apply this. Okay, so this is, again, what you would see on the homework. Okay, so the reason we do this is because if we can get a sample of data and the sample is symmetrical, that means we can use the mean and standard deviation in these ways. Now, there's more sophisticated uses of mean and standard deviation. That's statistics. That's not course one. So this is just basics, how you use the mean and standard deviation. So say we want to measure a larger population. Like colleges may want to measure the incoming freshman population. A business might want to measure its potential customers. Or government tends to do a lot of surveys too. Like a lot of economic statistics is basically a large sample. Why is that? Because it's really too expensive to measure every single person, right? If you're a cafe and you want to maybe branch out into a new neighborhood, do you want to talk to every single person who lives there? Well, you don't have to do that. So you can get reliable data from a sample, and then if the sample is symmetrical, then you can do this stuff. So that's how this is helpful. So we got to sample people in San Francisco, and we have the average age of 45 and the standard deviation of 12. Okay, so for number one, you want to do 55 minus 45 divided by 12, and then 25 minus 45 divided by 12, and then 15 minus 45 divided by 12. Okay? And so if we have our mean of 45 and our standard deviation of 12, calculating the z-scores for 55, z, 25, and 15, that's just these calculations. Data value minus mean divided by the standard deviation. Now, for the first one, it's going to be positive because 55 is more than the mean, whereas for the next two, you're going to be negative because 25 and 15 are less than the mean. Okay, and then the last topic here would be one standard deviation interval, which is 68%, three standard deviation intervals, which is 99.7%. So this is where we're going to add one standard deviation of 12 to the mean of 55 and subtract. And we're going to add three standard deviations of 12 to the 45 and subtract. Okay. So for the 68%, add 45 to the 12, 57. Subtract 45 and 12, 33. Okay, well, if we multiply 3 times 12, we get 36. So three standard deviations involves adding and subtracting 36. So if we add 36 to the 45, we get the upper end of the interval, which is 81. And if we subtract 45 minus 36, we get the lower end of the interval, which is 9. Now in practice, we tend to make this or equal to. It just makes it easier to deal with. Okay, so what does this mean? From the sample that maybe the city of San Francisco decides to use to get a sense about the demographics of the city, because you only do a census every 10 years. The city may be deciding to do some policy with Muni, and so it may want to know the age distribution because older people tend to rely on the municipal system more often. Okay, so here 68% of the city is going to be in this range of age. Okay, whereas 99.7% of the city is going to be in this range of age. So only 0.3% is less than 9 or greater than 81. Okay? Everybody good with that? Okay, so there's not a lot of homework on this. I think maybe 5 problems. You can see if you're doing the z-scores, it's not a huge calculation, but just enough so we can learn the basics. Okay, so I'll tell you what's on the assessment this Monday. It's basically everything that we haven't done the rest of this unit, but I'll go ahead and put that on the Google Classroom just to make sure everyone got the memo. Okay, y'all? Anybody need anything? Next week, our class is going to end on Monday. You're welcome. Yeah, that's what an assessment is, Darius. It's a quiz, not quite as long as a test. Okay, is that good, y'all? I'm glad you asked. Okay, I'm gonna go ahead and get out of here. Y'all take it easy.